Welcome to this video. My name is Mark Scythian. The date today is July 30th, 2024. This video is going to focus on alternative power concepts that I've been working on over some years. There will be multiple parts to the alternative power concepts videos, and in this video we're going to cover concepts 1 through 4. So the first concept is the solar steam turbine power plant. So it's set up where we have 1,000 solar panels sourcing off of 50 houses with 20 solar panels each. And of course our inverter efficiencies are very high today, right around 95%. So let's assume we tapped sufficient power, 171 kilowatts transferred into a steam boiler, for which we set the saturated steam enthalpy at a steam temperature of 316.25 Fahrenheit, a very practical steam temperature dynamic, or let's say steam dynamics steam temperature. And so based on a rough scenario calculation set, we're able to input 190 kilowatts of AC power from the solar panels and then discharge 241.7 kilowatts of AC power through a separate generator. So how this works is 1,000 solar panels as a test prototype, and we want to be efficient. We don't want to have all of these facilities built everywhere, so we can just tap them off of the household system that's already underway across the United States. So just assume we have 50 houses with 20 solar panels each and 95% inverter efficiency. We're about 200 watts DC per solar panel. So when we do the computations, we're able to harness 190,000 watts of AC true power from the solar panel cluster sent through a power distribution grid. And then if we take that electrical power and use saturated steam enthalpy amplification, we can then send the electrical power to a closed system steam turbine that includes the discharged steam to be condensed and returned back into higher temperature water, returning back to the boiler. So then we conserve water as well. And so the 190,000 watts of AC true power then goes through 90% electrical efficiency through the wiring, leaving 171 kilowatts of AC electrical power. So then if we were to send this through the wiring through the boiler system, that's about a 4% loss in electrical power. The electrical power is converted to thermal power using an electric heating element, and then thereafter we have about an 80% thermal transfer of the heating elements thermal energy into the water with given industry standards of boilers. So then we have 0.8 times that product, and then divided into 1056 watts, the number of watts to 1 BTU per second. So this leaves us with 124.36 BTUs per second. So we can vaporize almost half a pound of water per second. So if we vaporize 1 pound of water per second, that's about 1.2 million watts of steam power. So we have about half that value. Then, because it takes 289.39 BTUs of heat to vaporize 1 pound of water from any temperature above freezing to the 316.25, or any temperature below boiling point 212, but above freezing point to 316.25 degrees Fahrenheit, will require 289.39 BTUs per pound of liquid enthalpy. That's based on the steam tables. And then once we get that steam at the 316.25 degree Fahrenheit dynamic steam optimization temperature, we then get a return of 1184.2 BTUs per pound of total saturated steam enthalpy, but we can only absorb 20% of that steam at the turbine. Let's see, where did I have this? I think I have to populate. Yeah, so we have 20% steam turbine efficiency. I did not write that here, but this should be a 20% steam turbine efficiency. So the steam power itself, only 20% of it can be converted to mechanical power at the turbine. So that's been factored into the calculation here. So we have the 124.36 BTUs per second divided into 289.36 BTUs liquid enthalpy, and then that ratio is multiplied times 1184.2 total enthalpy of steam power output, and then we know that 1 BTU per second is 1056 watts of power. So this these summations here, except the 0.2, would be the actual steam power, but when we push that steam power against the turbine, then we can only get 20% of that steam power into mechanical power. So we end up getting 360 brake horsepower off of vaporizing approximately half a pound of water in 1 second at 124.36 BTUs. That's taken from the 171,000 watts of AC power harnessed from the solar panels. And so the return is 241,704 kilowatts of AC power, because this 360 brake horsepower then turns this AC generator, which would be like a municipal city grid generator, something that could power more than 50 houses, or a set of houses, supplemental or primary power, either way, depends what the demand is. And so we're able to harness, because of the amplification of steam enthalpy, we're able to harness 241,704 kilowatts from 190 kilowatts of AC output or input power from the solar panels to the boiler's heating element. So that's only about 50,000 watts more. But if you look at the big picture, with accumulating every kilowatt possible in the long run based on demands being at a specific time during the day, maybe in the morning, maybe in the evening, not too much at night, this concept would pay itself off after prolonged use, because once we conserve much of that available power output, return power from the AC generator, the 241.7 kilowatts right here, most of it won't be used anyway. It'll be overproduced. So the rest of it can then go into charged capacitive cells, which through enough of an infrastructure and charge time constants in its capacitive cells could have enough available power to keep this boiler running throughout the night, but then we would have considerably less power demand at night statistically. And so by the time daylight arrives, this thing would then return its power to its theoretical full capacity, and it would just keep running. There'd be very minimal losses in water, depending on the type of labyrinth seals to keep the non-ideal gas of steam separate from the water, separate from the air. And it is a very tricky business with steam, because at a high enough steam temperature, even rock can be melted with steam. But we're not going to something crazy like the 500 Celsius or 1070 Fahrenheit. We're keeping it at a low enough steam temperature with high enough steam dynamic power. So 316.25 is a very optimal temperature. And so it would be a pretty long life cycle, perhaps several years at a time, before any major maintenance is required. We could also have a sequential secondary system to run in unison, so if there's any downtime, the power would still be running with a secondary system, and then it could be incrementally maintained. So this is just the test cell design of experiment to test the concept. So even at a very experimental level, we're getting a pretty good power return with the saturated steam enthalpy amplification. And this obviously does not violate any laws of thermodynamics, because we are dealing with a different animal that is the non-ideal gas of steam power. So supplemental steam power amplification from a solar DC to AC source is actually very practical, cost effective, and I don't see it on the market, so I thought I would publish this and spread the idea. Perhaps we could get together, whoever wants to work on a project together, perhaps a joint project to maybe build a smaller version of this. Aside from that, everything else is funding and politics and et cetera. But the science is here, and we just have to put the feasible concepts together in a little more strategic manner. So this is called number 1, the solar steam turbine power plant, and there are solar turbines that are out there, solar-based steam systems, and give or take, there may be a different way of amplifying other than steam or other than charged capacitive cells, etc. But it is a premise to share with respect to alternative power concepts. So that's the first one. Second one is, scroll down here, and this has to do with harnessing centrifugal force to incur piezoelectric power output. So we would have a rotor with arms, and inside of those arms there are hollow tubes made of reinforced stainless steel, or something that's reinforced and flexible. So we could say stainless steel or perhaps graphite. We're not really picky on if it's a conductive surface, but we would just have a hollow structure that may or may not be hinged bearings or hinged roots. And so the primary rotor turns. We could also power this rotor off of solar electric power. So we get enough RPMs and enough mass or weight and enough of an arm. And in this case, if it was spinning at 1,000 RPMs at a 4-foot diameter, we're not too concerned if the tips go supersonic, but we would keep it under a tip speed that is not supersonic. So we'll just assume 8-foot diameter times pi, so there's 24 feet per revolution. So 24,000, perhaps it should be a little bit shorter, but let's say we got the RPMs down to 600. So if we just had shorter arms and 1,000 RPM, let's say we had some adjustments, at face value the centrifugal force would be 13,660 pounds of centrifugal force, which would then push on the blue component here, the weight. It's spring loaded, so it's spring loaded outward, but that's just for support and placement of the 0 point. And then when this starts to rotate, the centrifugal force builds up, and that would be 13,660 pounds centrifugal force across a 3-inch diameter weight channel or weight diameter. And so that's 7.07 square inches. So we could push about 1890 pounds per square inch upon a piezoelectric circuit. And because there is more respect to capacitance and current, or we would just say current, current is correlating with pressure, whereas voltage is correlating with displacement or velocity or motion. So we wouldn't get much motion here. We may get some compressive piezoelectric effect. So piezoelectric circuits are pressure stimulated electron discharge. You could see these types of circuits even on weigh scales or whatever. So enough pressure goes on the piezoelectric circuit, it's going to discharge a current. But the challenge, the criticism of that application for power generating is that it's consistent with a rate of change of increased pressure. And so consideration for making a constant pressure piezoelectric circuit is feasible. It takes some research, but if sufficient current can be continually discharged instead of over a change in pressure while at constant pressure, harnessing a very exponentially efficient force, in this case centrifugal force. There's so much potential in harnessing centrifugal force because it doesn't take much RPM, much of an arm, and much weight to incur some massive amounts of centrifugal force. So why not channel and harness that upon maybe a transistorized piezoelectric circuit, which has the ability to switch on and off the subtle pressure differentials. It wouldn't be perfectly constant, the centrifugal force, and from that, perhaps an inductive capacitive resistance, RLC, perhaps inductive field could be switched on and off and create at least maybe a high voltage surge or high voltage grounding to the stator rotor electric brushes. So there are things to take advantage of, especially with the irregularities and fluctuations in the centrifugal force and the pressure. So perhaps a transistorized piezoelectric circuit would actually make the electrical power output quite practical. Now, how much are we going to lose to run the motor? And there isn't. Okay, so we're going to have a ground to the brush that also creates electromechanical resistance and torque in the opposite direction. So that has to be solved. Perhaps ceramic ceramic brushes, or a ceramic commutator brush assembly, or at least a brush assembly, or perhaps it could be a brushless assembly in the likes of a DC brushless generator. There's other ways to consider, but the main point is that we could derive an electrical power source from pressure stimulated electron discharge, i.e. piezoelectric circuit, and then derive that from centrifugal force. So that's something to consider. This has been placed into drawings before. It's nothing new under the sun, so it's often forgotten about, so I thought I'd bring this one up here. Let's see, the next one is, probably many of you seen this before, but this is what Gap Power was working on. Again, a lot of these applications have already been developed or at least invented. They haven't been streamlined, and they haven't been at least on a accepted market, but we have the magnetic amplification and neutralization reciprocating magnet system. So here we have one magnet, neodymium magnet, which is reciprocating. It's a linear reciprocating neodymium magnet, and it's on a rail moving back and forth right here. And then we have a second magnet here, which is stationary, and within it, or at the end of it, within the clearance for this moving magnetic piston, which is connected to a flywheel using a connecting rod of some sort. And so it comes very close, but it does not obviously hit the stationary magnet. And so at the clearance range in front of the magnet is a DC coil with very fine, high gauge, thin copper wire, maybe 4,000 or 5,000 turns on a reel. Just a simple input-output, positive in, negative out. It's a DC system. And there would obviously be a diode to keep the flow one way, and there could be a charge circuit with another diode. And so what happens is that we have a DC power source, maybe a battery, and it sends the electrical charge to the coil. And with a sufficient electrical charge, DC electrical wattage, we're able to neutralize this stationary magnet's magnetic field, so that when the piston, the moving magnetic piston, reaches in close proximity to the stationary magnet, it has no repulsion magnetic force, and then the reciprocation can continue undisturbed. But right when the dynamic magnet is moving away from the neutralized coil, there's a cam breaker that cuts the DC electrical power to the coil, and then this stationary magnet remagnifies to full magnetic repulsion, thus pushing and reciprocating the dynamic magnet to then deliver torque and RPM to the flywheel. And the other premise is that when this magnet is moving so fast and suddenly, and then we neutralize the magnet with an external power source, a DC power source, we're also having the ability to charge electrons breaking off of the lines of magnetic flux from the dynamic magnet into that coil, and that's where we need another secondary charge branch circuit with another diode to then send some electrical charge back to the, let's say, a battery DC power source. So at least there is some power recovery, and but the issue is that we can't create or destroy energy. We can only convert it or change its form. So we don't get something for nothing. Even magnetic neutralization, with these strong neodymium magnets, there would be considerable DC power in order to neutralize what would be even several hundred pounds of magnetic repulsion. And so that is correlating to the foot-pounds per second mechanical power, and that is correlating to mechanical wattage, and then that goes and correlates with electrical wattage. And the fundamentals of magnetics may or may not exist outside of the laws of thermodynamics, but when dealing with a material or a structure, even though within the field and within the lines of magnetic flux we return back to a material, so something is going to have to give. And more than likely, under recent experiments, the heat is actually going to be an issue. So there may be a huge consideration for making a super high efficiency magnetic amplification reciprocating power plant to focus on the development of ceramic materials for as a dielectric for as a thermal dielectric. So we can have electric insulation and conduction, as well as a heat sink, all in one material, which somebody has actually worked on and developed. So with all that DC power needed to neutralize a very strong magnet on the stationary end, it's going to cost substantial power. And so the next consideration is, if we have enough mass to the moving magnet and we have a strong enough magnetic field, which we do on the moving magnet, we're possibly able to charge a considerable amount of the DC power lost in the form of the mechanical reciprocation, sufficient to break the lines of magnetic flux, and then charge a substantial amount of electrical conversion from that mechanical motion back into the coil, back through a secondary branch circuit, through a opposition flow diode going to the battery source. So a considerable amount of power lost from the battery could be charged returned. But then again, when we come out of the lines of magnetic flux and the inductive field, we then have a material to deal with, and then it becomes the laws of thermodynamics, which are relevant to both the matter and the energy. So it's not just the conservation of energy, it's also the conservation of matter under the first, second, and third laws of thermodynamics. And there is both the quantum and the classical laws of thermodynamics in the 0th law of thermodynamics. So again, all the numbers and the equations add up, but then the material science might be off. And then there's great success in this device. However, then the heat builds up, and then the rates of change of power return start to fluctuate and drop. And so there is a huge room for improvement. But bringing the concept out, this isn't your electromagnetic solenoid sewing machine or jackhammer. This is something a little bit more than just a magnetic reciprocating solenoid. It's something that can use a DC coil to neutralize magnetism and then also charge on the other direction as the dynamic magnet advances forward and then starts to break its lines of magnetic field, while the other magnet is its magnetism has been neutralized. So there's a lot going on in such a few components that those who have worked on a system like this, just from the basic reciprocation like a solenoid, and then building it up into a charge generator, a solid state system on the charge side, just a coil, and working with the rapid switching probably has to be transistorized, and then they run into the heat because you don't get something for nothing. So a lot of heat's probably going to build up, and then you run into, oh, we got it working, but it's not practical because no matter what we do, it heats. So there's probably a consideration with material science to actually make this type of a magnetic amplification-neutralization flywheel power plant practical. But if so, and efficiencies can be increased substantially, then it becomes something that can run indefinitely with the right materials at just at constant RPM, constant torque, or something that's a constant RPM system. And then you can have other systems drive off of it, like an AC generator, or perhaps a constant speed drive, driving hydraulic and pneumatic pumps, and etc. This could also be used to pump oil out of the ground at lower cost. You know what I'm saying? So if it takes 5 barrels of oil and equivalent crude oil to drive a gas turbine engine to then pull oil out of the ground, and let's say you get 16 barrels out of 5, this could substantially increase the amount of oil that can be harnessed. And remember, we're not using oil just for combustion and fuel, but all of your plastics, all of the other non-fuel, non-power, or non-combustion related products are all made from oil. Your plastics, your fertilizers, you can name it, synthetic wood, the asphalt to make roads, etc. So, oil is not just for fuel, but it's for just probably more applications, synthetic drugs, etc. That is all made out of crude oil. So that is a high commodity practicality in the oil industry, and anything to reduce the cost of mining oil means that you can reduce the cost of mining anything else, because it's all going to require energy. So keep this one in mind. And then the last application in this part 1, is I have about 25 different alternative power concepts to share, and so this is the first 4, and so we move on to this is the 3-dimensional helical corkscrew hydrodynamic rotor. And the basic premise is that a corkscrew drive rotor is far more efficient than a 2-dimensional axial flow rotor. So if we had a hydrodynamic rotor, something like an axial flow blade set driving or accelerating water flow, we could improve on that rotor and make it 3-dimensional, much like a rotating corkscrew. And then we don't have to make its diameter very large. It could be as little as 1/8 the diameter of that tank. And when we introduce 3 dimensions of rotor propulsion into a fluid medium that is relatively dense like water, we are also able to increase the amount of foot-pounds per second at the outer radius because the circumference is greater, and we have a relatively similar amount of mass, but then we have a consideration to accelerate that mass into a higher final velocity in a practical amount of time. So we're able to more than likely harness greater hydrodynamic power at the outboard or outer radius part of the tank using minimal rotor power because of the geometry of a 3-dimensional corkscrew rotor. And then at the end point of the tank, of course with water seals and everything, we have a water turbine, more than likely centrifugal flow, paddle type turbine, a radial impeller that derives a significant amount of torque at lower RPMs to then go to drive a generator. And so that corkscrew could be powered by a low power electric motor drive, or a low power electric motor could drive a corkscrew, and low power as in a moderate amount of torque at a minimal amount of RPM. And again, it could be also powered off of the solar panels, solar power. And so once this thing gets going and runs at constant operation, constant speed, etc., we can have a very good return on the efficiency to drive some higher current, higher torque, lower RPM generator, and then everything else could be sent to transformers to flip that around, increase the voltage, decrease the current, etc. So keep this one in mind, and this is just a helical corkscrew hydrodynamic rotor. I think this concept was heavily researched in the 70s out in the country of Austria in Central Europe, and this was off the premise that actually I think it was a musician, a statistician, and a physics major kind of took the idea of the geometry in nature and the correlation with resonant frequencies and sound, and then they kind of just devised that into what would be its equivalent material structure. And it's the common sense approach because nature is efficient but simple. So yeah, it always finds a way to be very powerful no matter what opposes it. And so out of that, the natural rotor is what they called it, was the helical corkscrew type drive rotor. So they actually did build a little water tank, put this tiny little corkscrew rotor about 1/3 the height of the water tank, and they drove it at very low RPMs, relatively moderate torque. And the result was this large water quantity started to efficiently rotate, and it reached a lot higher in outboard speed than expected. It actually became what we would say considerable. So we had almost a vortex building up. And of course, you'd have a vortex wanting to build up in the center, but it would build up around, and then the corkscrew 3-dimensional rotor would dissipate those turbulent flows, and then they would encounter some centrifugal force and go outward. And to their amazement, this water would start rotating in a very powerful manner from such a small, low RPM helical rotor driving and amplifying the acceleration of hydrodynamic motion. And then at the end was a centrifugal or radial flow impeller, and they did drive some really excellent amounts of power output for the amount of power they were putting into this corkscrew rotor. And so some of these are actually still around in Central Europe and in other parts of the world, and probably experimental places around the world near universities. I think the Japanese were working on something like this. And so you can set up a bunch of these grids, these power stations, and they are zero emissions, they're quiet, they're subtle, they drive out a lot of power, and they run on, can't get something for nothing. So nothing's really free. There's no real free energy. It's just how much of that power we put in do we get out. So this is really high efficiency, fewer moving parts, quiet, clean. It can also be made cosmetic and artistic. So you might think you have some work of art, but it's actually a power generator sitting around all the cities. And it doesn't take very much maintenance. I mean, you might have to put some screens and meshes in here, vents, and maybe you could inert and antibacterialize the surfaces, so the maintenance and the cleaning of the water and all these things are minimal or to very non-required for long periods of time, and you end up getting a pretty good power return, all because of the geometry of this rotor. So keep this one in mind. It's called the three-dimensional helical corkscrew hydrodynamic rotor, and that is the long title to describe a rotor in a different language and culture. They give it a name, but it is just a three-dimensional helical corkscrew, and it could be improved upon. So that's 1 through 4. It's a little detailed, but what counts is getting the concept. So we have many more alternative power applications. There's also the now water electrolysis, turning it into hydrogen and oxygen. I mean, if we do it through standard electrolysis, it will take 6.7 watts of electrical power just to get 1 watt of hydrogen combustion. So, I mean, it is feasible and anybody can make hydrogen gas, but you might as well just use the electricity instead. But where making hydrogen from water is very practical is when hydride, this is hydrogen 3, metallic hydrogen, and when you're using solar power and hydride, then it's very easy. It takes extremely low electrical power, solar to electric, to produce a large amount of hydrogen gas from water. But the only problem is the Department of Energy allows anybody to make hydride, but it takes quite a lot of centrifuge time to actually reach a third isotope of hydrogen. And hydride is typically used in nuclear facilities, especially experimental nuclear weapons, because the dreaded weapon above nuclear weapons, other than directed energy, is the hydrogen bombs, and not one has actually been used. They've been science experiments, but they're way more devastating, using hydride, water to hydrogen, and then you can actually induce thermal and nuclear fission, implosion of atoms, as well as thermal incendiary together. And so hydride is an easy way to make very cost-effective hydrogen from water, except the politics behind actually purchasing hydride is illegal to the public. It's illegal to those not qualified in Department of Energy regulated nuclear facilities, and we'll just say in the nuclear power and the nuclear weapons industry. So those are only reserved for people cleared security clearances in the DOE facilities. And we know that the DOE is we tend to think the DOD is really massive, but the DOE is even larger. So all of these feasibilities exist. It's just that the public, I don't know if they're raised awareness to maybe form research projects together within legalities, right? So again, hydrogen gas itself does not have a lot of energy density. about 1/3 that of methane. And so, but it is clean burning. We can get water out of the emissions. And so, yeah, if you can make hydrogen really quickly, cost effectively, other than vaporization, something like through hydrolysis, but the Japanese or the Honda company in Japan have made a practical hydrogen engine using compressed hydrogen because its molar mass is so low and not as effective for BTUs per pound energy density. But there's a trade-off on that. Whenever you have a gas with such a low molar mass, really, really low molar mass, you have the ability to compress that gas into much higher extreme pressures. So with the potential energy pressure alone of taking liquid hydrogen, quickly vaporizing it into hydrogen gas, with expansion close to 600 times its liquid volume into gas, you can quickly pressurize a high pressure tank. The ones they built at Honda was a 5 to 6 year project to develop it, and it could stop I think 4 or 5 anti-aircraft rounds. So that tank alone was a substantial part of the research. So that's an extremely loaded tank, something like 125,000 psi and 14, 15 gallons. It's kind of crazy. But if you were to discharge the brake mean effective pressure per every power stroke, so that would be a 2-stroke compressed hydrogen gas engine piston, then it is very practical. So they perfected it over in Japan. I think they get about 230 miles to hydrogen gas fill up, and if they harness the hydrogen gas from hydride, then it would be super cheap, which I think they did. So there is a regulatory commission on the economic end on how much displacement of a current economic model. So there's going to be a limited amount of, or zero amount of imports of the compressed hydrogen gas. But so there's a lot of people that have been into alternative power can recite a 5-hour thesis on every alternative power application. And some viewing this video are probably like saying, when is this guy going to stop? I got to talk about the hydrogen, And yeah, with combustion, there isn't much energy density, but if it's cheap to make the hydrogen from water using hydride, you could just fill out the liquid water, and instead of combusting it, you can compress it. And another design challenge with the valve train for compressed hydrogen, or for combustion of hydrogen gas, is that due to the molar mass of hydrogen being so small or low, it's almost impossible to develop a valve train that will actually consistently seal the hydrogen gas in the combustion chamber of the reciprocating engine. So it's probably, unless material science is already advancing exponentially, but more than likely you couldn't do it with a poppet valve system that actuates. Not for any long-term reliability. Maybe safety, yes, but reliability, no. So it's a safe engine, but then you go out of business because nobody wants to buy the product. It's junk, right? So reliability is probably a no-go for combusting hydrogen inside a valve train system. But compressed hydrogen gas, yes, you can really make that happen, because as the compressed hydrogen gas expands, then it's going to react with the oxygen in the air. And again, you get H2O out of the reaction. So it is zero emissions. But that's just a few things to cover. So I almost, out of the 25, I'm probably gonna scrap about 10 or 15 of them, because either you don't have the hydride for the hydrogen for electrolysis, and now it's not cost effective, or we've reached the threshold in rigorous design of experiment, computational parametric modeling, to the point where something is not practical or something is losing more energy than gaining, because you tend to find the correlation between practicality, cost, ease of manufacture, repeatability, other than the design concept itself. And so this really heavily falls into the next notch up above your typical mechanical and electrical engineering, and that is the material science engineering, which is more or less in the physics and mathematics realm. So if you wanted to do material science, then it's probably better to major in physics or mathematics or even chemistry or physical chemistry, etc. But it doesn't mean and mechanical, electrical, aerospace engineers can't get more into the material science and push that limit of quantum materials research and make a material come forth that makes these concepts actually practical and cheap, safe, cost-effective, reliable, repeatable, etc. And then we have the big breakthroughs. But these are design concepts, so there is total 25. I could probably X about 10 out because we haven't reached the research needed to actually come up with a material. So this leaves us with 15. We subtract 4. So that's about 11 more concepts I could make in 2 more videos. But keep these in mind, 1, 2, 3, 4. So just a little recap here is solar, steam, turbine, power plant. This is amplification of saturated steam enthalpy to a steam turbine from solar panels. The centrifugal piezo-electric generator, so that's pressure stimulated electron discharge derived or sourced from centrifugal force of weights inside canister. Magnetic amplification-neutralization, and we are essentially trading mechanical power for charge, electrical charge, at the expense of magnetic field by a supplemental DC power neutralization of a magnetic field, and then a return field when the field collapses on the cam breaker shutting off. So all in all, we are probably recovering a substantial amount of the power lost to keep the system running. So at the very least, this becomes a high efficiency electrical power plant or mechanical to electrical power plant. We could just say it's a mechanical power plant with a flywheel. And so the consideration is that all the equations in mathematics work out, but then there's such a rapid change in multi-cycles that the materials will probably fail, and much of the accrued efficiency will be lost as heat increases. And so whether it's mechanical, electrical, thermal, sound, etc., it's all different power transfers, and everything comes back to zero in the thermodynamic conservation of energy, right? So, but it is just the basic concept, something more than just a sewing machine's solenoid or jackhammer's electromagnetic solenoid, something a little bit more that adds a charge field to a coil, as well as neutralizing that magnetic field for practicality. And then lastly, we have the three-dimensional hydro corkscrew rotor to then amplify a substantially greater amount of mass contained in a fixed geometry, that of a cylinder, rotating and reaching greater and greater hydrodynamic power output and potential. So the last part, more alternative power concepts to share at a later time, to be continued. Thanks for watching part 1 of Alternative Power Concepts video. Thank you and have a great day.